loud. Let's pull it away. Okay, well, thanks for bearing with me for 3 long lectures, and now we're in number 4. I felt like the last one was maybe a little bit heavy, pretty much targeted at the theorists, I guess. But let's. I feel it's pretty essential. It's sort of the one, really, in some way, deep theoretical result that has actually really led people to work on this area. It was developing this continuum model that led to the prediction of these magic angles, which is what motivated the MIT group to actually push hard enough on this difficult task of actually making samples like this to start seeing this phenomenon. So last time, I spent basically the entire lecture trying to derive this, oops, it should be minus here, trying to derive this continuum model. I'm writing it in a slightly different way here. Instead of introducing yet another Pauli matrix, which might be giving you nightmares, I just decided to write explicitly the layer. So in this continuum model, we have, for each valley, we have a 4x4 matrix. Okay, it sort of looks like the usual Dirac equation here for each valley, except the 2 Dirac points are shifted. This is the Dirac point shift due to the rotation by an angle theta, and k theta is just proportional to theta, that angle. But on top of it, there's a periodic modulation of the tunneling, which basically locally shows how the system changes locally from AA to AB to BA hopping and something in between. And that tunneling matrix has this kind of nice form like this. Basically, symmetry alone led to this model just having 2 parameters that we didn't know. Call them V and W here, changing U to V for all you nice people. By comparing to what we know for untwisted bilayers, we expect that V and W are quite similar. Maybe due to vertical relaxation, the V will be a little bit smaller than W, but both should be of order 100 millivolts. The only other parameter in here that is dimensionful is the Fermi velocity, which we can take from ordinary graphene. Okay, so this thing is this is just a one-particle Schrodinger equation, which is periodic. Qj are the Q0 is 0, and the other 2 are just 2 basis vectors, reciprocal lattice vectors of the Moire zone. So this is like a Bloch theorem problem. And so you can just use Bloch's theorem to find the eigenstates. I won't do it because it's actually hard. Okay, in general, it's hard. It becomes hard. It's easy in a certain limit, so there's this parameter, alpha, which if we take V over W fixed of order 1, the only remaining dimensionless parameter is alpha, which is W over VK theta. If this is small, the problem is easy, but then basically the Dirac cones in the 2 layers are not perturbed. When this becomes of order 1, greater than of order 1, it becomes a hard problem with sort of a strong periodic potential. But in general, it's not hard to solve on a computer. What you could do is the nice thing, what people usually do is do a plane wave basis. So you just write wave function as a sum over plane waves. You sum over reciprocal lattice vectors, call them little q here. Each one has an amplitude. Okay, so we know that a Bloch state is a plane wave times a periodic function, so you can think about it as starting with a given momentum state k, and then Bragg scattering to all the reciprocal lattice vectors, which are shifting these by q, and each one has an amplitude. Here, this is just a spinner, so it's just a 4-component vector. So that state could have amplitude in either layer and on either sublattice. Okay. And typically what you do is you truncate to some, you consider all the wave vectors less than some cutoff, which you take to be large enough that the thing converges for the bands that you're considering. All right. In fact, you know, down to the first magic angle, you get pretty good results keeping only 3 values of Q. Okay. And in Bistreitzer and McDonald, they actually do part of the calculation for 3 values of Q analytically. You can't calculate the whole bands analytically even for that. If you think, so they consider, effectively they consider 4 of these components, 4 2-component size, so they end up with an 8x8 matrix by doing this. And you can say certain things about it, and you can already approximately get the first magic angle from that. But I won't do it. Many people have been asking me now, are you now going to explain where the magic angles come from, why they're there? And the answer is no. Okay, I'm not. I don't know. Nobody really knows. But this isn't a hard calculation. You can put it, even I could put it on a computer, even in Mathematica, some very lightweight software. You can write this thing. You can probably do this in, I don't know, 10 or 20 lines of code or something like that. It's not difficult. And yeah.
There was a paper by Ashwin and some other people claiming that in some model you have an exact flat band. Is that at all relevant?
Well, I'll tell you. So I don't, because I want to cover a lot of things beyond band theory, I don't want to spend a lot of time with this. There are, of course, attempts to understand it. Some of the work we did with Chunshao is also an attempt to understand it in a different way. What Ashwin and his collaborators did is they studied the model with V equals 0. Oh, sorry, this is about 1, not 0. Okay, that if you take the model with V equals 0, so this thing here is 0, it's in the class of what we call chiral symmetric Hamiltonians. The Hamiltonian has a special structure. It basically becomes, in some sense, purely off diagonal. The only tau matrices that appear are tau x and tau y. There's never a tau z. Whereas this, here we have kind of things on the diagonal. Anyway, in that case, there's some degree of solubility. Even that's not totally solvable, but that has exactly flat bands. The problem is that's not really close to this model. So the people think that maybe the correct ratio might be 0.9 or something like this. Okay, 0.8 or 0.9, not 0. I don't know that it really has that much to do with the physics of the real systems. But
sorry, could you just remind me quickly what the V and W are?
there. Is that what you wanted? Yeah. They're the.
Oh, actually, no. Actually,
So V is like the hopping if you had an AA ordered system, and W is the hopping if you have AB or BA. Okay, and so they're basically the same because they're just hoppings between 2 PZ orbitals that are aligned on top of one another. That's why they're basically the same. Okay. Only difference is that actually in the AB region, the layers come a little closer together. That changes the hopping a little bit, but this is a very small effect. Okay, so that's intuitive. That it should be like this. Okay, so you put this on a computer. It's not hard, and you start seeing, nice things. Okay, I'll show you some of the nice things again. Okay, this is experiments. All right, we'll need this. So what I want to do is just summarize. I'm not going to show you tons of band calculations. What I want to show you is what should you take from the band calculations, because now we want to get, most of today should be spent on the interesting stuff. What are actually the correlated interaction effects in these twisted bilayer graphene? So what are kind of the salient features of the continuum model? Okay, so I would say the first obvious feature of the continuum model is there are always band touchings. Basically, and almost always Dirac points at K Moire and K prime Moire. So these are the corners of the Moire-Brillouin zone, okay? you know, roughly speaking, the reason for this is we saw that Dirac points are stable if we don't break this kind of inversion symmetry or time reversal, and the model doesn't do that. So they're locally stable, and they're pinned to these corners by threefold rotation symmetry. So as you smoothly deform the model by changing the angle, always means as a function of theta, okay, or alpha. I'm going to call this thing alpha. I'm sorry. Yeah, alpha. Okay. Alpha is this dimensionless parameter. All right, that's what you actually vary when you do numerics. There are always band touchings and Dirac points at k and k prime. Okay, and at all angles. Yeah. Okay. So for large angles, just a comment. You know, twisted bilayer graphene has been around a long time. It's only the very small angles that are new. You know, for a long time, people knew that if you had AB or BA graphene, you get this quadratic band touching. But sometimes maybe you want to study two graphene layers that are just close in space, but which almost don't interact with each other by hopping. So they're very interesting physics, things like Coulomb drag that people studied a lot in 2D electron gases, where you have two really nearby 2D electron gases, but there's no tunneling between them. So in the old days, twisted bilayer graphene at large angles was viewed as a way to do that. If you twist at large angles, the two K points are so far from each other in momentum space, there's no way to transfer from one to the other. So effectively, there's just no hopping at low energies. Okay. So large angles, of course, then you just have a Dirac point in each layer, and it's perfectly stable. So large angles kind of clear. And you know, this is an experiment. This is from the MIT group, Pablo Herrero's group, from a couple of years ago, before magic angle graphene appeared, of a, you know, still pretty small angle, but bigger than the magic angle, which is around 1 degree. Okay, this is close to 2 degrees. And these are Landau fans. Okay, this is the diagonal resistivity as a function of magnetic field and density being tuned by a gate. Okay, and you can see these lines here, which correspond to motion of Landau levels. And this is the Hall resistivity. You can see the same thing here. So by fitting these, they arrived at these Landau fan diagrams here. Okay, and maybe you probably don't remember the numbers from before. Okay, I showed you on the blackboard what this should look like for single layer graphene, and you may remember the integer quantum Hall effect has these funny series of plateaus: 2, 6, 10. So plateaus are spaced by 4 and symmetric around 0, and that was the signature of Dirac fermions with 4-fold degeneracy. 4 because 2 for spin and 2 for valley. They form, each spin in each valley forms a series of Dirac Landau levels, which sort of intrinsically has a series of a half, 3 halves, 5 halves, and you multiply that by 4 and you get this. This is actually twice that, okay? So this is a half, 3 halves, 5 halves multiplied by 8 rather than 4. Why? Because it's a bilayer. So we have 2 for spin, 2 for valley, 2 for layer. In this Moire picture, the layers are actually mixed because there is tunneling between layers now, but still the original Dirac points, one from each layer, sort of survive, but those correspond now in the Moire picture to the 2 Dirac points at the corners of the Moire-Brillouin zone. So we drew this picture. If this is the Moire-Brillouin zone, and these are, if you remember, this kind of the original Dirac point was here, and one of them rotated here, and one of them rotated here. This is K and K prime. So if we turn off tunneling, this becomes a Dirac point in one layer. This becomes a Dirac point in the other layer. But even as we start mixing them and these wave functions start becoming mixed between the 2 layers, the Dirac points survive at K and K prime. Yeah?
As you've shown yourself before, I mean, the point is that once you have decoupling, and even at these larger angles,
Yeah.
as compared to the magic angles, you will have a Fermi singularity that couples the 2 of them. I mean, so while the Dirac points remain stable, there is a saddle point relating them, which is at rather low energy still. So the experiments here seem
Yeah.
So in principle, you would expect, it was seen actually also in another experiment before, by from Klitzing group, that above a certain magnetic field, when these lambda levels start to see the Fermi singularity, actually it goes from nascent to generous down to full.
Yeah, so, I think the logic here is, you're right, of course. So first of all, transport is a very low energy probe, much more low energy than kind of tunneling, for example, probes. And in principle, if we want to probe, we're really trying to just use the magnetic field as a probe of the zero field state. Most of the physics we're interested in here is actually zero magnetic field physics, trying to find some correlated system. Maybe it's Hubbard model-like or something in twisted bilayer graphene. So we want to stick to very small fields. When you have very small fields, as Amalia talked about, you have really kind of classic quantum oscillations where there's no magnetic breakdown and things like that. And then we probe really the lowest energy physics, and you can hope to probe the states near the Dirac cones. But indeed, as if you crank the field up, these are, I think, they're pretty low fields. You crank the fields up, you start seeing other things, and just to tell you, okay, the theory says this. If you actually do the same experiment in magic angle graphene, okay, now this is one of the more fundamental results from the continuum model. You should still have these Dirac points. So at the lowest fields, the lowest energies, you should see this sequence. Remind you what it was. Okay, it was, let's just look at it here. It was 4, 12, 20, all right. What do they actually see? Well, here's some experiments from, there's same data from MIT group, but these are my friends, so I'm showing their data, okay? It's later. Andrea is in my department. They see 4, 8, 12. It's not the same sequence, okay? This is not the sequence you'd expect for these Dirac points with spin, valley, and Dirac point or layer degeneracy, okay? And this is Dima's experiments, okay? You also see 4, 8, 12. He seems to see a 2, okay? Not even quite the same, all right? I think everybody sees the 4, 8, 12, 16, more or less, in this vicinity. So no one sees the quantum oscillations you'd expect from the non-interacting continuum model theory, all right, just from the lowest energy states. So there are many things that could be going on. It could be because the bandwidth is so low, states that are not at the very lowest energies are mattering, as you say. Or it could be interaction effects, or it could be some other effect, like I think you mentioned earlier that these systems all have boron nitride encapsulating them, which actually breaks some of the symmetries, depending how well aligned it is. So maybe one of these degeneracies is split. In my opinion, evidence is accumulating that, so this is a fan emanating around charge neutrality. So this is what should be probing these Dirac points connecting the conduction and valence bands. I think evidence is accumulating that interactions are very important here, maybe more important here than anywhere else, actually. This is where they observe the biggest gap created by interactions in pretty much consistently every experiment. Great, continuum model is great. It gives us some qualitative reason why we should have narrow bands in this region, tells us where to look for magic angle, but it's already not explaining this, okay? Which is basically the simplest attempt to directly probe band theory. Okay, good. Now I'm going to hide this again and up. I got it. Yeah. Okay. I shouldn't have put it away. All right. More general lessons. Okay. General lessons is the velocity. So we know now that we know that we have Dirac points, we know that the velocity at the Dirac points is an oscillating function of field. Wrong one. You're going to be doing a lot of work. A function of angle, sorry, not field. Okay, and so that's what I could show you a real plot, but let's not do it. It looks something like this. Okay, velocity versus angle, with this first angle happening around 1. This is 1 over angle, I guess. This is around a half. I don't know what this is, 0.3 or something. I'm making it up, so I don't know what it is. Okay, you can find this sequence. Okay. And a priori, we don't care all that much about the velocity, but it's a bit of a signature. If you have two bands that are dispersing linearly around 0, and their slope is smaller, probably the bandwidth is smaller. And in fact, if we were to plot bandwidth on the same plot, it would look kind of similar. It comes down, gets narrow for a while, comes back up, comes down, gets narrow for a while, comes back up. It looks something like this. Okay. So there are these regions where the bandwidth is very narrow. And there we should expect that the system is very easily perturbed by interactions. All right. The third salient point, which is maybe the most important if you're trying to actually think about the implications, is that the details on the scale of the flat bands themselves depend on the details in H, on small effects in the continuum model. Okay, so now I want to show another slide. Okay, let's leave the lights on. I think you can see it fine. Okay, so this in particular is some very nice work. Again, basically before the experimental discovery. Okay, these guys were trying to improve a little bit on the Bistritzer-McDonald model. Nam and Cucino. Cucino is an old hand in graphene area. What they studied is the effect of lattice relaxation. Mostly the effect is the one that I mentioned, that in the A, B regions, the layers come a little closer together. It's a pretty small effect. You're changing this V from 1, V over W from 1, like what McDonald used, to, I think, 0.8. Okay? So the red curves are actually the Bistritzer-McDonald results. Okay, so here is at, let's look, I don't know, this one. Here's 1.05, which is, something that people like to call the magic angle. So, you have these pretty narrow bands here. So this scale is EV, so this is 50 millivolts here. This is the two Dirac points, K and K prime. In the center here is the gamma point. Okay, so you can see the bands, conduction and valence bands touch here. This is around one valley, okay, at K and K prime in the red curves. But they come up actually and touch the next higher bands, okay, here and here, okay. So actually in these calculations, without this lattice relaxation, there's no gap to the next band. You actually have touchings to the next band. If you allow this lattice relaxation, this level crossing gets pushed away, and the band becomes relatively well separated, and in their calculations, they find a gap, not within the two bands, but between the flat conduction band and the next conduction band of something like 12 millivolts. Okay, and another gap in between the valence and the next valence band. Okay, and these kind of effects are important. They'll find they're kind of important, at the magic angle and somewhat above, but become much smaller if you go up to 2 degrees or something. But this is a big effect, right? All the physics we're studying is on the scale of these flat bands. It changes their bandwidth and changes a lot of features. Okay. Yeah. That's not the lattice. That's the tunneling. Okay. Yeah. It's not the distance. That's in energy units, okay? Let's see, I think that says stop, so I should stop. All right. I don't remember what the next slide is, though. I'm really curious what the next slide is. Show me what the next slide is. I'm going to peek. No, we don't want that yet. Whoa, what happened? I don't know why I'm not showing it. Okay. Great. Okay. I feel like I should show it. I'm going to show it. All right. So that's theory, right? Here's some experiment. Okay. This is a very recent experiment. We'll come back to it later. It'll be important later. But this is STM from a group at Caltech. This is a plot of differential tunneling conductance from a STM into twisted bilayer graphene. This is a bias voltage, so the voltage between the tip and the sample, and this is a backgate voltage, again, varying density. So to map it out for you, in this region, the Fermi level is inside the flat bands, but they can go above. Up here, the Fermi level is actually in the next band, so this is sort of the cartoon here, okay? In this green line, the Fermi level is up here in the next bands. These bands are much wider, so they're basically uncorrelated. So that kind of two-dimensional quadratic band has a constant density of states, and so that's why these lines have almost constant slope here, okay? A couple of features. So these features here are associated with, now you've set the bias. You can see you have a pretty big negative bias over here. Negative bias is enough to allow an electron to tunnel from one of the flat bands. Up here, the flat bands are fully occupied in the ground state, okay? It's possible to now for an electron to tunnel from one of these flat bands into the tip, okay? And basically, these two features are kind of associated with the Van Hove singularities near the top and the bottom of these two bands, okay? So the separation here gives you a rough idea of the bandwidth of the flat bands. Now, it may seem a little weird, especially to the students. Why would I go to this very high bias voltage, gate voltage, to bring my Fermi level really far from the flat bands to measure their width? Okay. So the reason is what we would like to have is a measure of the bare width of the bands without interaction effects, which can, this is a strongly interacting system. If we put the Fermi level inside the flat bands, the thing we measure with the STM is no longer the single particle density of states. It's it's not the band theory density of states. It's some complicated many-body object, the one-particle Green's function, which, for example, DMFT likes to calculate, okay? Up here, with the Fermi level up here, these bands are now very far from the Fermi energy. They're just fully occupied. So they are not correlated at all anymore, and we can just measure the actual energy it takes to extract an electron from one to the other. And the difference is a best measure we can get of the width of the bands, and it's something like 20 to 30 millivolts, okay? If you look on the plot, so they can identify this kink here, identifies when the Fermi level as a function of gate leaves the upper band, and down here, it's less well-defined, I would say. Some drastic stuff happens when the Fermi level starts entering the flat bands. Okay, so we kind of expect drastic stuff to happen down here because now these flat bands are starting to become active and the strong correlation sets in. Okay, Pierce?
Those bands are like hundreds of times narrower than the original graphene bands.
Yes.
You would think that the mass would be far higher given the band narrowing.
I can't, but I'm not showing you the Haas van Alphen data.
I know, but it is a spectroscopic probe of those Moire bands.
It is, but that's not a, so again, that's a dressed quantity. That's a quasi-particle quantity when we actually have the Fermi level in the bands. And so we're in the regime where strong correlations and all hell is breaking loose. And
Strong correlation makes the mass dimensional.
I understand.
Why is it doing nothing to the mass, or in fact anything, making it smaller?
Yeah, I don't know. I don't know. There's a ton of stuff that's not understood here, okay? I'm trying to make a point that even the band theory level things are wrong, okay? Okay? Well, it's not so bad. This is kind of roughly okay, okay? The quantum oscillations, you can worry about the mass of the quantum oscillations, but even the oscillations themselves are wrong, okay? Okay, so this is a line cut showing you the difference here. It's again showing you sort of qualitatively how big these interaction effects are. If we had just a pure band theory system with no interactions, the only thing the gate does is shift the Fermi level. So when that happens, the bias plot should just shift to the left and to the right as you vary the gate voltage. The shape should be the same. Okay, so this red plot is a cut up here, okay, basically. So this is when the band is very full, and you're seeing these Van Hove singularities. Yeah. No. It's not a momentum resolved measure, so maybe you're thinking in terms of an ARPAS measurement or something like that. And this is a very broad thing. I think there are many reasons for the broadening. Among other things I'll mention, these are quite inhomogeneous systems. But I think the effect you're really seeing here is something like a Van Hove singularity. It wouldn't be sharp in any case. This is not something that in any measurement would be a delta function because it's just a local density of states. So I think it's quite difficult to extract a mass from this. Okay, but that's a good question. Other questions? So this is, the same system just gated to some region around charge neutrality. And it's very different from a rigid shift. You can see there's a much bigger gap here. There's some sort of mini gap feature in here. There's clearly much more broadness in the two Van Hove singularities. So all that are interaction effects. Okay. Great. All right. I think I can lift this up for a moment. We'll do a little talking. More student questions? Okay. So, this continuum model, this band theory is interesting. So, it's really interesting to some theorists. So, I think there are kind of what I would call theorists' issues that a lot of theorists find really fascinating. If you spent, years doing topological band theory, you might find these really interesting theorist problems. So let me mention a few of them. Bless you. So if you actually plot the electron density of, for example, a filled valence band, what it looks like is it's kind of has smooth peaks in the AA regions. This makes a lot of sense from our local picture. The AA regions, if we had perfect AA graphene, they're metals. It's kind of metallic puddles, whereas the AB regions are semi-metals, so the kind of electrons you would think would try to avoid the AB regions and mostly go to the AA regions. Indeed, also if you take a block state at, for example, near the Dirac point, it will also have peaks in the AA regions. However, if you actually try to build Vani functions, so if you take, first year solid state physics, you learn about Vani states. These are these localized states that you build by basically, you form a wave function, which is a function of x, by summing up block states. In this way, you can sort of build a block state which is centered at some position near R. But if you build you have to choose phases for these block states, and if you do this in the smartest possible way, you build what are called the maximally localized Vani functions. They have a center where their center mass is. And the center of mass actually not on the AA sites. Okay, it's kind of weird. If you have the Moire lattice in real space, okay. So this is not graphene now, all right. You have the AA region here. And these are maybe AB and BA. The Vani centers are actually here. Okay. And so what one of these Vani states looks like is kind of weird. It's got very low weight at the Vani center, but has symmetrically distributed lobes out here. So, a nice term that Adrian Poe, who's one of the people who worked on this, used is that they look like fidget spinners. Maybe you play with those, okay? Okay. So this is kind of a hint of something strange going on. Usually people, theorists, when they try to construct type binding models, work with Vani states. That's the best way to construct type binding models from a band structure. Okay. I can't hear you, sorry. Can you speak up? Oh, this is the Moire structure, okay? So these are, this unit cell contains, 10,000 carbon atoms. So if you should forget about the atoms, right? Yeah. It's an emergent honeycomb lattice if you want, okay? I don't know whether you say it. I mean, honeycomb and triangular have the same Bravais lattice. They have basically all the same symmetries. So in fact, there's a really theorist issue. It's hard. You can guess from this it's going to be hard to write a type binding model. So I showed you some pictures of these bands, from this Nam and Cochino paper. They show you have a band like this, another band like this, and they have some bands here. In their picture, these are pretty small. I've probably drawn it not to scale. There's kind of a pretty good size gap here and a pretty good size gap here. As a theorist, you're crying out to, maybe any physicist would say, we should only care about these bands, and we get rid of these upper and lower ones. And so the usual story in condensed matter physics is a flat band. If it's flat, it means there isn't long-range hopping because it's very narrow. If it's narrow, there isn't long-range hopping, and so it should be a good candidate for a type binding model. Unfortunately, it's very hard to write a type binding model that captures these bands. Okay, and this is somehow goes under the name, some not very well-defined thing as far as I can tell, fragile topology. A lot of famous people, including this young guy, Adrian Poe, Ashwin Vishwanath, Andrei Bernavig, writing a lot of papers about this, telling you basically it's hard to write a type binding model. And the sort of best they can do to write type binding models to try and capture these two bands is they say, well, we actually can't do it, and we have to write 8 or 10 band models that capture a lot more bands, ones that we don't really want. Okay. It's very hard to find physical implications of this for the experimentalists who'd like to know what does fragile topology mean to me. As far as I can tell, it means almost nothing. It just means it's hard for theorists to simplify the problem. We don't like to work this continuum model already pretty hard. So.
Are the points 2 and 3 related? The fact that the 1-year states have that structure?
I didn't number the points, but yes, they're related. Yes. Yeah.
One question: when you try to use your 1-year states to derive some finite models, you basically have this freedom to choose like a triangular structure or this hexagonal structure in order to right?
You don't really. You don't. The Vani centers are defined once you, if you demand you want to fix the symmetries and you fix a specific band. So you should do a little bit of counting. Okay, we really don't have one flat band. We have 2 because they touch at conduction and valence. So each one of them we have to form some Vani states. And of course, it's not totally well defined because they touch. So that's part of the problem. In fact, I think the root of the problem, roughly speaking, but only roughly speaking, the clearest root of the problem is that both K Moire and K prime Moire have Dirac points of the same sign, of the same chirality. So this is why in just, for example, AB bilayer graphene, when you let the two Dirac points talk to each other, you end up not with an insulator, but a quadratic band touching. Around that quadratic band touching, the Hamiltonian winds twice rather than once. So they somehow, the whole band, even though it forms a band, is still chiral somehow. And I say somehow because I don't know how to make it perfectly well defined. Okay. On the other hand, this is really a theorist problem, okay? Because theorists, 8 years ago already wrote down a model which perfectly describes everything, all the bands, and it's only because the theorists want to simplify it to one or two bands that they're running into this issue. Okay. So, yeah. You can account for an insulator. We can decide whether we call it a mod insulator or not. Yeah. So what we can do, if you mean mod insulator in the sense of breaking no symmetries, then no. We have to break symmetries in the band theory to get an insulator. You need a band gap.
But also something that's well localized.
Well, I'll give you an example. It's a question of what you call a band insulator. Okay, you can get a band insulator which, whether or not you call it a churn insulator is an example, where it's not possible to consistently write a complete set of Vani functions that obey all the symmetries. So that you can certainly get here. If you can, at certain fillings, you can also get insulators which do not have a churn number. So these are very possible. But you do have to break symmetries.
Meaning that the notion of a localized moment in a mod insulator won't be well defined in these systems?
I don't know. It's a good question. I think it can be, frankly. My feeling is, so the sense is that this obstruction to writing a type binding model is very restricted. It's very tied to this notion that we have Dirac points at K and K prime, and these are quite fragile in some sense. So the real systems have this, they always have boron nitride on them, which actually breaks this C2T symmetry, which protects these Dirac points. As soon as you do that, there's no longer any fragile topology. That's already gone. Okay, it's completely known that is removed entirely. And then I have well-separated bands. I can form Vani states. There's no issue. So this may be, I suspect, this physics is probably important at charge neutrality when you're really close to these things. Most of the physics people have been studying is, at half filling, three-quarter filling, quite far from charge neutrality. I don't know how important it is. Yeah.
Perhaps just to mention to build on that, this is, I think, a crucial issue in this field, because what we are doing here, the correlated states that we encounter here, which are just concerned actually with one single band. So it is clear that you cannot localize everything, because in order to have a true localization, you need to take into account all the bands, which means a deep going back to, a U which is enormous. However, this is like in Landau levels, if you want. You cannot exactly localize, but what you can do is you can localize on a particular length scale, which in the Landau level would be given by the magnetic length. And in the churn insulator, you can do something similar. So the question is how to write down afterwards localized states. But in terms of those localized states, I think we can talk of the model.
Yeah, I think there is an issue here which is not fully understood. Just maybe for the students to be clear, when we talk about a localized state here, we mean can you think about electrons localized to basically one unit cell of the Moire pattern? That's what we're talking about, which is huge compared to lattice scales. Okay, it's not clear to me whether this means that there is actually some obstruction to forming a localized mod insulator without breaking these symmetries. Okay, and I've asked all these guys this question, and I've never got a straight answer. They basically don't know. Okay, this is only, as far as I know, this fragile topology is just a statement for the band theory. So I just want to mention this for the theorists. I really regard this as a theorist issue, not an experimentalist issue. At this point, we need a theorist to come up with even one experimental consequence of this fragile topology. I should say Andre Bernevig proposed one, but it was wrong. Okay, maybe he thinks he can still rescue it, but that's...
The main problem is charge the balance.
No. We'll get to that in a second, okay? Good. Give me 5 minutes to get to what I consider the main experimental problems, okay? All right, so these are things that are kind of related to band theory. Now we can get to experiments, okay? I'm going to show you some stuff again. Go back to the screen. Okay, so there's lots of quantitative issues in experiment, as I showed you here, what's going on. This is very different from what band theory would predict for the single particle density of states. Can you calculate it? Okay, that's, in my view, a little bit too quantitative a question. We should try to ask some question that has more clear physics in it. So now we're talking about moving away from this model. Let's ask about, what are the phenomena? Okay. Better chalk. All right. Dimitri already gave you, pretty great overview of the phenomena. Let me condense it. He gave 2 whole lectures, so let me condense it to like 2 slides. All right. So I would view there, in broad classes, what are the issues? Okay. The first issue, maybe, roughly speaking, is what are the ground state phases of twisted bilayer graphene. Really the full in experiment, okay? What we know from experiment is that there are a number of insulators where we don't expect them. They're correlated, they usually call them correlated insulators. And these seem to always occur at integer fillings, meaning what I would say, I call the number of electrons, the density of electrons, meaning the number of electrons divided by the number of Moire unit cells, is 0, plus minus 1, plus minus 2, plus minus 3. Okay. So that's those are these vertical colored bands here. This is temperature and doping carrier density. Okay. None of these correlated insulators would be expected from the continuum model of band theory, any of its simple variations. Okay. These could be, many possible interesting states. They could be magnetic, antiferromagnets, ferromagnets. They could be charge density waves. They could be quantum Hall states. They could be striped. They could be pneumatics. Okay, we have various bits of information about them. Some of them appear to be from experiments. Some appear to be ferromagnetic. I'll talk a little bit about this. In between, and these happen, at pretty well-defined densities, mostly in between. One sees superconductivity. And these are Dimitri's results, more or less drawn in cartoon form here. You can see for the most part the superconductivity he finds is between these correlated insulators, although even this is not studying a lot of samples. I don't know how many, maybe 2 samples are used to put together this diagram, more or less. And even here you can see sometimes there's superconductivity overlapping where this correlated insulator is. Sometimes it just obliterates it. I would say the early experiments made it look like the superconductivity was only occurring near the doping of this particular correlated insulator. I think the more recent experiments show that is certainly not a general result. And we don't know a hell of a lot about the superconductivity other than that. There are a few details, a few interesting features, and then there are things that are sort of generic to two-dimensional superconductivity. I think there's no doubt that bilayer graphene is two-dimensional, so it's not so important to prove that point. So these are, I want to emphasize, these are sort of ground state questions, very low temperature questions. They're addressing low temperature properties of experiments, we know from correlated electron systems that often high temperature properties can be interesting. So there's a lot of nice work on normal state transport. Again, I'm being very biased and showing my friend's data here, so this is, if you looked on Dimitri's plots, this phase diagrams, when he shows as a function of temperature is usually going up to a few degrees Kelvin, all this identification of correlated insulators and superconductors is measurements below about 5 Kelvin or so, but of course you can measure these things up to room temperature, or maybe not quite, but so these are scales up to here. This one's up to room temperature, here's up to 150 Kelvin. I don't have a lot to say about this. Some people have made a big deal about seeing linear in temperature resistivity in this regime in some samples. Here it is, kind of linear temperature for a 2-degree sample. Here's kind of linear in temperature for around 1-degree samples. All I want to say is there's a vast amount of data to be mined here. It's really beautiful. Try to think for yourself of an ordinary solid-state system where you can, in one sample, or even in many samples, vary the carrier density from over a range of 8 electrons per unit cell and more. Vary the temperature from below the Fermi energy to even several times the electron bandwidth, and measure the resistivity. So this should be like a playground for anyone who thinks they can really understand transport. So this is, the bandwidths are, remember I told you the bandwidth of these narrow bands are maybe 10 or 20 millivolts, so that means 100, 200 Kelvin. So these are temperatures bigger than the bandwidth, actually big enough that you can start to see effects of exciting electrons into the higher excited bands. And you can see, beautiful things like the change in sign of the Hall conductivity from hole-like to electron-like, and track how that happens at higher temperature. This is associated with activating electrons into the next band. It's amazing. So, also, I thought Pierce would like this because he likes metals. Okay, good. I'm going to put this up again. So, that's just a recitation of experimental results. I'll say a little bit more about details. How should we think about it? So, the short answer is, nobody actually knows, all right? Basically, only the band theory is understood and not much more than that, but okay. We can start talking about plausible other explanations. Let me talk about a little bit about interactions. Even here, I should say, we know these effects are not described by band theory. We need to add something, and there are two obvious things to add. One is electron-electron interactions, and one is electron-phonon interactions, okay? I have a bias. I don't like electron-phonon interactions. It's boring. But it's probably important. It might be the reason for the superconductivity, okay? So, and some people believe that. I think it's pretty likely, actually. But it's pretty unlikely that correlations are the reason for the insulators. That electron-phonon interactions are the reason for the insulators, so probably that's related to electron-electron interactions. So I want to focus on Coulomb interactions. So here there's something we can say, which is what the form of Coulomb interactions should be in this type of system. Again, this calls back to the idea that everything in these Moire systems, and indeed everything in graphene, is very low energy. Okay, so there is some low energy Dirac approximation. This should be valid in the spirit of Fermi liquid theory, that we're studying physics on an energy scale much smaller than the bare energy scale of the width of our bands, and also the bare energy scale of the Coulomb interaction of two nearby electrons in real space. Both those energies are huge, even in graphene. And single layer graphene, we know that band theory kind of works, but there are interactions. How do we describe them? So what I would claim is this is a kind of very simple example of Fermi liquid theory, FLT, which in a slightly more modern view, although you don't need to be too modern for this, slightly more modern view, I would say that Fermi liquid theory is an example of what we would call an effective field theory. These are just fancy words for saying we should be able to write down an effective continuum Hamiltonian which only describes the physics near the Dirac points. Okay, and that effective Hamiltonian should be that of, have a certain form, and I'll write down. So what should it be? Well, it should be the one electron part, which is basically the continuum model. Okay, let me start simple. Let me talk about actually one layer graphene without any twisting. Okay, this is the simplest example. If we measure single layer graphene and we don't take temperature up to 10,000 Kelvin, we don't dope, to 10 to the 18 carriers, we're studying energy physics near the Dirac points. And so we know that for non-interacting electrons, a good approximation is this just Dirac equation, but those electrons interact. And so in the spirit of Fermi liquid theory or effective field theory, we should just add interactions to this Hamiltonian, okay? And this is a time-proven method that you can rely on. So what are these interactions? What interactions could we add? Well, we can do a couple of things. We can add short-range interactions, which generally look something like this. Yep. I had this before. You kind of, it was not tau, I'm sorry. Mu, I guess. Yeah. I should just write H Dirac. It's not important, okay. Anytime I have a question, I made some mistakes. I think that's a fair assumption. So we can write local interactions like this, which involve, 4 fermion operators, so this is like some 2-particle interaction, and they're with some matrices in here, and I don't even want to specify what they are. Could be anything, okay? Lots of different interactions could be there without a detailed calculation. It's hard to know what they are. But in addition to this, there will always be long-range Coulomb interactions. It's an index.
Yeah, exactly. But what's it
1, 2, 3, labels these terms. An arbitrary number of terms that I'm not writing down. My first matrix might be tau z. My second matrix might be the identity. My third matrix might be mu x tau y. I don't know how many matrices I can write down, probably. Okay? Just an arbitrary label, okay? The reason it's arbitrary, and I'm not worrying about it, is these are going to, I'll argue in a moment, they're not very important. Okay? Okay. The second is what looks like the ordinary Coulomb interaction. Okay. So let me say a few words about the philosophy of this thing. How do we arrive at an effective field theory description? How do we arrive at this Dirac equation? Well, you already saw how we arrived at it for band theory. What we did is we solved the full band theory, and then we threw out the states outside of some small momentum window around the Dirac points. In general, the way we do this with interactions, we imagine, quote, integrating out these degrees of freedom outside the cutoff, okay, outside some low energy window. That's what effective field theory is. We sort of take into account the effects of excitations of high energy or short distances and leave only the low energy ones. And in doing that, we generate corrections and things to the Hamiltonian. That's what these are. You know, bare electrons, if we start with the fundamental theory of interacting electrons in the solid, they just have Coulomb interactions. Okay, there's no such thing like this. But by integrating out electrons, for example, in higher bands and those outside some circle around the Dirac points, we'll get these type of things. Okay? But we'll always have this, and the reason is that Coulomb interaction is long range. So even if I mess around with short distance stuff in my solid, if I actually build a puddle of charge in some region, that charge has electric field lines that extend infinitely far away, and they'll be felt by another bit of charge over there. So you can never remove the long-range Coulomb interaction for the total charge in the system. That's why even in a metal, for example, the long-range Coulomb interaction has an effect. It creates the plasmon mode. Okay. These are not metallic systems, so this has to always be present. So now we can do just a dimensional analysis exercise. Okay. We can ask, on dimensional grounds, how big should these G's be? Okay. Well, our graphene system really has one length scale in it. It has the lattice spacing. The only microscopic length is A0, like an angstrom, kind of distance between two carbon atoms. It's a fraction of an angstrom, really. And we can form from that an energy, which is the Coulomb energy. We may want to put a dielectric constant in here because our graphene is sitting in some environment. It's a dielectric constant of the environment. Okay. What's the dimension of G? Well, these M's are just dimensionless matrices. Okay. So psi dagger psi is a density in 2 dimensions. It has dimensions of 1 over length squared. So this has dimensions of 1 over length squared. This has dimensions of 1 over length squared. There's a 2-dimensional integral, which has dimensions of length squared. For the Hamiltonian to have dimensions of energy, the dimensions of G have to be energy times length squared. Okay? So the only quantity we can build with those dimensions is E squared over epsilon A0 times A0 squared. So we expect G to be of order E squared A0 over epsilon. Okay? It has to be. There's nothing else it can be. Now, let us ask, how does that actually compare to the long-range Coulomb interaction? Okay. It's a little difficult to compare because, you know, this one's got 2 integrals in it and this has 1. So there are various ways to compare, but let's, a simple way to compare is let's, you know, suppose our charge density is slowly varying. Suppose we can approximate. There isn't much physics in this. I just it just allows us to compare apples and apples instead of apples and oranges, okay? I want to make this term look like this term. So I'm going to approximate this by psi dagger of x, psi of x, okay? If I do that, then I can take my h Coulomb Oh, I should put a screening length on here, okay? And let me add a screening length. I'll do it here. So in general, there'll be some screening, usually from nearby gates or something like that. We shouldn't expect this screening to occur on any length scale shorter than the Moire pattern. Okay. Imagine it's going to be much bigger than the lattice spacing of graphene, clearly. Okay. And then I write this. Okay. So now I can actually do the x prime integral. Nothing else depends on x prime. Okay. So I just do the x prime integral. Well, okay. What is that? We go to radial coordinates. We get 2 pi here, e squared over epsilon, dxx divided by x is x prime. I take some coordinate. Let's call r. I let r equal x prime minus x. Take from 0 to infinity, e to the minus r over psi. Okay, radial coordinates, we get 2 pi r dr. We cancel these r's. You can see this integral is an easy integral to do. It's just equal to psi. Okay. So, life is reasonable. We got something with the same dimensions as G. Okay. Now we can compare. What's left is the same form as G, except with the 2 matrices here being just identity matrices. Okay. But there's a difference in the scaling. This one's multiplied by this length psi, and this is multiplied by A0. Okay. And so what this means is that kind of if you want the size of the Coulomb matrix element Coulomb interaction compared to these short distance interactions is psi over A0. Okay. And if psi is big, kind of characteristic size we should take is something like the Fermi wavelength or the size of the Moire unit cell or a screening length. It's always much bigger than A0. That means it's the long-range Coulomb part that's important, and these are negligible. So in certain band theory calculations, when people do DFT to study like donor levels in semiconductors, this is called a central cell correction. But if any of you, work through the chapters on semiconductors in Ashcroft-Merman or Cattell or whatever your favorite book is, you learn like the energy levels of a donor in a semiconductor, and you solve it by solving the problem of a hydrogen atom. So you assume that electron has Coulomb interaction with the ion. Okay. When people study the electron gas in 2-dimensional semiconductors, all of the theory of the fractional quantum Hall effect, you assume that 2 electrons in a semiconductor interact via ordinary Coulomb interaction. But they're actually electrons inside a solid. They're described by some effective field theory. It's an assumption that they only have a simple Coulomb interaction. Okay, they don't really. Okay. But this same assumption is true here, maybe even more so because the Moire pattern is so big. Okay. So the one basic thing that you should know is that in the continuum model, you can, to a first approximation, describe the interactions between electrons as just density-density Coulomb interactions. Okay. Everything else is a small correction. And so we can directly apply that also to twisted bilayer graphene. Doesn't simplify our life that much, but a little bit. So we know that our Hamiltonian for twisted bilayer graphene should be something like the continuum model plus just Coulomb interactions. Maybe something, if I take Coulomb interactions, it could be a little more complicated because I have to consider both layers. There's probably a half here somewhere. and be some screening length. And then times the where this thing is the total charge density. Summed over layers and valleys. Okay. Can everybody make out everything here? So this is a simple thing. It's just the density-density interaction with 1 over R form extended to the two layers. You know, there's a little bit of subtlety here because the electrons in 2 layers are separated by a small vertical distance. But I think this is probably also not important because this distance d is like 2 angstroms, so it's still awfully tiny compared to the Moire lengths, which are, 10 nanometers. So I think probably this is also unimportant. Okay. On top of this, there may be very small kind of local corrections like this, but I think they can be they're very unimportant. Okay. So this sounds like a simple, maybe obvious statement. I don't know how obvious. Who thinks this was obvious? There, yeah, kind of obvious. Good. I don't know. Anyway, but it has consequences. Okay. In particular, what's important is symmetry here. If you really think about this object, if I were to write it out, there would be a sum over layers, a sum over valleys, and a sum over spin. Layer, valley, spin. And sublattice too, okay? There'd be some sublattice. I'm going to leave that explicit, okay? And so it's really just a total density operator, right? So this object is actually very symmetric, and it's invariant. The density is invariant under a separate SU2 rotation for each valley. And a separate U1 rotation of the phase for each valley. Okay, it actually has, this is invariant under even more than that, but those are the important ones, okay? So this means actually the spin of each valley is separately conserved, and the number of electrons in each valley is separately conserved. Okay, that's the physical content, okay? So for these long-range interactions, very good approximation. The symmetry group is SU2 cross SU2, starts to look like the standard model, U1 cross U1, which means basically separate spin and valley conservation, spin and number conservation in each valley. You could try to propose other symmetries like rotating layers into one another, et cetera, but those are broken by the quadratic Hamiltonian. So these are the only ones that are present for the whole Hamiltonian, including both the continuum model and the interactions. Okay, so this is sort of unusual. Usually in electronic systems, spin might be a good quantum number if you don't have much spin orbit, and charge, of course, is a good quantum number. Okay, so we have more symmetries, so more complicated, interesting things can happen as a consequence. Yeah.
Just ask a question. Why is it SU2 plus SU2 and all that stuff? Why isn't it just SU4?
Because the quadratic Hamiltonian doesn't preserve SU4. So the Hamiltonian for the two valleys is different. Okay, because one is like right-handed moving Dirac points and one is left. Yeah, okay. So that's why. Okay. Yep. Good, okay. So that will have an implication. And that's, beyond that, there isn't a hell of a lot I can say about interactions. Good. Okay. I can again. You can ask what do you do? So there's certain things that theorists like to do. One thing you could try to do is you might try to project the Coulomb into the flat bands. So this is something we learned to do a lot in the quantum Hall effect, where you have perfectly flat bands, Landau levels. And that the logic of this is if you have some bands that are pretty flat, and then you have other bands up here and down here, if this gap is much bigger than the Coulomb energy, that's something like, E squared divided by epsilon times the Moire length, then it's very hard for electrons to get scattered from one band to another, and we can throw out the occupied, and this also needs to be big, and the empty bands, and just focus on the flat bands. Okay. Well, I showed you the data. Okay. It's not really satisfied. Okay. It's about the same order of magnitude. So I don't know. Theorists still want to do it. Okay, because it makes life simpler, maybe. Doesn't make life that much simpler, because I challenge you to actually take that Coulomb interaction and project it into these awful bands where we don't know how to write a type binding model or anything simple. So it's theorists can try to do it. They try to do it. We don't know how good it is. Okay. Beyond this sort of calculational thing, there are more conceptual questions. Okay, so we can think of at least two conceptual approaches. And these conceptual approaches are sort of in the philosophy of something that Giovanni mentioned, I think, in his second to last lecture, which is this dichotomy between Mott and Slater. People have probably heard this story, okay? It's really a matter of debate, I think, right now, how one should think about these twisted bilayer graphene systems. So one possible way, which is kind of a la Mott, we try to think about twisted bilayer graphene the way we think about strongly correlated transition metal compounds like the cuprates, okay? And usually we think about something like a Hubbard model. So we would say, well, could we approximate our system of pretty flat bands, of narrow bands, as some kind of hopping of electrons on some lattice? Maybe it's a honeycomb lattice here, or maybe it's a triangular lattice of the AA sites, I don't know. And then mainly some short-range interactions. Should be sum over orbitals, Ni alpha, Ni beta. We give some large energy cost to doubly occupying orbitals. Maybe we think of one orbital per AB region, or one orbital per AA site, I don't know, okay? So we know what this kind of Hamiltonian leads to. It leads to chaos and pain. Well, okay, no, it leads to anti-ferromagnetism at half filling usually. It can lead to a lot of complicated physics if we have multiple orbitals. It leads to bad metals and pseudo-gap and who the hell else knows. It leads to problems we can't solve usually. It leads to people developing DMFT for 30 years and getting close now maybe to solving some of the problems on big clusters. I don't know, okay? So that might be the paradigm, okay? But as I mentioned, there are some issues. We don't really know how to write the type binding model. So this part of the Hubbard model we don't know how to write. So maybe that's a difficulty with that path. Other paradigm I would like to say is kind of a paradigm of Slater, but really inspired by the best understood flat band system, which is quantum Hall effect. In particular, I would draw a parallel to quantum Hall ferromagnets. Who knows what a quantum Hall ferromagnet is? Yeah, sure, our organizer, yeah. A couple people, yeah. So quantum Hall ferromagnet was some really beautiful physics around the time I was getting my PhD. It's been rediscovered in graphene, so that makes it maybe only 10 years old or something in that context. But the idea is you take a 2D electron gas with Landau levels, okay? And let's suppose that for some reason there's no Zeeman splitting, so there's no Zeeman interaction between the electrons and the magnetic field. So this is created by magnetic field. There's a big cyclotron energy, and we're going to take this cyclotron energy, very big compared to KT, big compared to the Coulomb interactions, the distance between electrons, which is like the magnetic length. So that's exactly the condition, you know, the theorists like. We can project out the highest Landau level. This is the lowest Landau level here. Okay. But now we consider, suppose our system is half filled. So we consider what's usually called total filling factor equal to 1. So it means that the number of electrons is such that you could fill 1 Landau level. Okay. So you're at a density. So remember, electrons have spin, so electrons, there's really 1 Landau level for up electrons and 1 Landau level for down. We don't have enough to fill both. If I were to actually put the Fermi level here, we'd fill both, and we'd have a Hall conductivity of 2e squared over h. That's perfectly well described by just band theory. But I put my Fermi level right here, right in the middle of these Landau levels. There's no gap. It's highly degenerate at the single particle level. I have to fill half these states. I could put them all in here, half in here, half in here. You know, exponentially large number of states. So it turns out that these systems become ferromagnets. And they're almost one of the best understood examples of ferromagnets. So they have less symmetry than these graphene systems, but they have, to a good approximation, SU2 spin symmetry. So whenever you have a symmetry in quantum mechanics, you can diagonalize operators that commute with the Hamiltonian. So the generator of this symmetry is the total spin, which is the sum over all electrons of the electron spins, or the integral of the spin density. Okay, and so this S total commutes with H. It means we can characterize our states by any given state can be characterized by the total spin quantum number. You know, as usual, S total squared is S total plus 1, and S total Z. Okay. And of course, the number of electrons is a good quantum number too, so we can also label it by the number of electrons. Okay. So if we fix the total number of electrons equal to 1, equal to nu total equals to 1, so basically this means n is the number of flux quanta piercing the sample. Just nu equals 1. Let's consider the state where the total spin is actually n over 2. So if I have n electrons, I can ask how big a spin can I make. The biggest I can make is n over 2. I just align all the spins together. That's degenerate, of course, because I could point my spin in any direction. But in fact, all those states have to have the same energy by SU2 symmetry that they form some big multiplet. So I can just as well choose the z component equal to this. Okay. And such a state with maximum spin is actually unique. Okay. There's only one state in the lowest Landau level. It's just, I take the product over all the Landau orbitals. For example, in Coulomb gauge, they would be the momentum in the transverse direction. And I put an electron in every state with up spin. Okay. So the logic is again like this in quantum mechanics. If I have commuting operators, I can diagonalize them simultaneously. And I choose this maximally polarized state. Since it's unique, it must be an eigenstate of the Hamiltonian, okay? So it's guaranteed to be an eigenstate of the Hamiltonian, even with complicated Coulomb interactions, as long as they just depend on the density, okay? So this is an exact eigenstate. It actually turns out to be the ground state, okay? Why is it the ground state? It's the ground state because for these lowest Landau level electrons, again, the Coulomb interaction, we can write as the integral, basically e squared over x minus x prime, the density at x times the density at x prime. This is the largest when x is very close to x prime, when the two electrons, we try to find two electrons interacting right on top of one another. If we have a fully polarized state, the Pauli exclusion principle prevents two electrons from getting close to one another. Okay, so because of Pauli, if the two electrons have, all the electrons have the same spin, we cannot never have two electrons in the same Landau orbit. So the ferromagnetic state completely excludes the short distance Coulomb interaction. And so that's the reason it's the ground state. Okay. Those of you who work on magnetic systems are probably familiar with, you take like a Heisenberg ferromagnet, this is something I do in a class too, maybe you had it in a class. Take a Heisenberg ferromagnet, you can show that the ferromagnetic state is an exact ground state of the spin S Heisenberg model. And then you also show that you can exactly obtain a spin wave excitation by flipping single spin. That's the same here. You can also obtain the energy of a spin wave excitation and show that there it's always positive, which is a good indication that this is a ground state. So this is well known in quantum Hall ferromagnets. The simplest example of a half-filled flat band actually becomes a ferromagnet. So it's an example where I would say basically Hartree-Fock is exact. In a certain sense is exact. Because this state is just a Slater determinant. It's one of the states you would write down for free electrons, but it's actually the exact ground state. Okay. So this phenomena is sometimes called flat band ferromagnetism. It's really proven in quantum Hall systems and probably basically nowhere else, but it occurs in a lot of theoretical models. It's been studied. You can get it on the Kagame lattice, for example. There's a lot of work by Mielke and Tasaki to prove these things for model Hamiltonians. Okay. So, this works for a flat band. What if the band is not perfectly flat? Okay, then it's complicated. Okay. The non-flatness of the band makes these statements much more difficult. Okay. You can still find an exact eigenstate. If you fill a band completely, it has to be an exact eigenstate, but it's much less obvious that it's the best state. It may be the best at optimizing the Coulomb energy, but it's not the best at optimizing the band energy. So generally, when you don't have extremely narrow bands, this is not what happens. Okay. So I would view these as sort of two paradigms, the Hubbard model approach, which leads to very correlated states, complicated states, a lot of degeneracy, usually antiferromagnetism, versus this kind of flat band logic tends to lead to ferromagnets. One thing you notice in this ferromagnet picture is the states that you form. I should mention, this ferromagnet has a gap. Why? Because, okay, our ground state now is a state like this. We filled every state of up electrons. Now suppose we want to add an electron to it. What do? Well, we have to give it a down spin, okay? But now you can see, that this statement is no longer true. Our downspin electron can sit right on top of the upspin electron. And so there's a gap. It starts paying that Coulomb interaction. You can't get away from the downspin electrons because they're everywhere. You end up with a one-particle gap, which is determined by the Coulomb energy. Yeah?
I think even when you have a slight dispersion in a flat band, it's not completely flat, the argument of the flat band ferromagnetism is still quite good.
It's quite good. Yeah.
You need to compare the bandwidth to the same.
Absolutely, yeah. So there's maybe I should say more about history. This kind of is an extreme limit of what's the old Stoner argument for ferromagnetism. So Stoner basically was asking, when do you get a ferromagnetism in Hartree-Fock theory? And in Hartree-Fock, you get a really good energy from Coulomb interactions, but you start paying energy that's proportional to the bandwidth. Because, if you had an unpolarized state, you'd put the Fermi level here. To make it polarized, you have to flip all the spins that were down here to up and stick them up there. So the Stoner criterion says that basically if the Coulomb interaction is much bigger than the bandwidth, you get ferromagnetism. We know it's not quite right because, here the Coulomb interaction is much bigger than the bandwidth, you get anti-ferromagnetism. So you have to be a little careful. I lost track of what I was thinking. I'm already running over, but let me look at my notes. That would help. I wanted to mention that if we go back to Dimitri's experiments, let's see where they are. This experimental data, all right. So this flat band sort of ferromagnet approach always approximates the state as some filled bands. So it can only ever give an insulator at an integer filling. Correlated states can give mod insulators at fractional fillings, like charge density waves and things, okay? But you notice in the experiment, it's always an integer filling, okay? Another point I would make very quickly is to say that, so in this, how would we apply this to graphene? A twisted bilayer graphene. So we have this picture that there are these flat bands. Okay, there are actually two of them that are they're touching in the continuum model. What would we have to do? Well, we would have to, first of all, we'd have to get an insulator, we'd have to split them somewhat. We'd have to open up some gap between them. Okay. Otherwise, even if we fill a band with one spin, we can still move it to the next band. And then we have to occupy, let's say, this valence band or conduction band. We have to form a state where we occupy every state in the valence band. For example, we take a product over I of all the all the K states in that band. And now I can decide, if I want to make a ferromagnet, I could decide I want to put all upspin electrons, and I also have to choose a valley. I'm going to put them in the K valley. Okay. So I could form a state like this. This is a state with 1 electron per unit cell. So that corresponds to -3 filling here. Right? I've only put a valence electron in. So if you think about forming a state like this, all the electrons come from one valley, and I made a gap for the valley. You may remember that we saw that if you open up at a gap at the valley, you get a Berry curvature. The valleys have a Chern number. So such a state actually generically would be expected to have a valley Chern number. Yeah, he's coming to stop me. And it would be expected to have an integer quantum Hall effect. Okay. And, that's, I think, probably the most exciting observation in this type binding twisted bilayer graphene so far is indeed the observation of a quantized Hall effect at this sort of filling. This is I'm showing my friend's data from Andrea Young's data from just a few months ago. This is at 3/4 filling. Okay, so it's kind of the flip of that one. At low temperature, they observe a very nice quantized Hall conductivity. It's quantized to 1 part in 1,000 in 0 magnetic field. Okay, so this is what's usually called the quantum anomalous Hall effect, and this is actually a much better observation of it than any previous observation, including in topological insulators. It's kind of cool. You can do amazing things with it. You can switch it with a current or a magnetic field at very, very low currents and fields. A lot of interesting things we don't understand about it. But maybe this simple Hartree-Fock flat band picture explains it. I don't know. Okay. Stop.